Welcome everybody if you're joining us on YouTube. So today is April 29th. This is Calculus 1, and we're going to do some optimization today. So the people who are here live, they've been thinking about this problem, optimizing the volume of this box. And what we're going to start today, we sort of finished up with this one last time. And the approach that we took was one via Desmos, right? So we set up our problem. We had our volume equation, and then we just kind of looked at it and picked out the highest point, and that was our maximum volume. But today what we're going to do to start is we're going to see if we can do this algebraically and see how that goes. And so if we remember, our volume function was this, right? So it was 10 minus 2x and then 15 minus 2x. Okay, so we had this, and then we plugged it into Desmos. And so where this came from was, right, so when we created our box, right, so we had a box that looked something like this, right, after we fold up our sides, and then this height is the height was given by x here, and then, right, so for each of these side lengths, what I had to do is I took away x on either side, and so for one of them we had, this was 10 minus 2x, and then this was 15 minus 2x. Right, so length times width times height, that gives us the volume of our box. Okay, so so for those of you live, anybody want to share what did we do? Like if I actually wanted to find the optimal value, what do we do? Right, so we're going to do this out algebraically. Like not with all the details, but generally, what are we going to look for here? If we're going to find a global maximum value, where do we look? Yeah, critical points, right, Emily? Yeah, so critical points and endpoints, right? So critical points are going to be our candidates. And then, so what we know is it may happen at a critical point, but it may also happen at an endpoint, right? So we want to check all those points, critical points and endpoints. All right, so so to check our critical points, what I'm going to have to do is I'm going to have to take the derivative of this function right here. And so if I'm going to take this derivative, what I want to do is expand this whole thing out, right? So that's going to be my first step here. Is I'm gonna expand this. I'm gonna multiply it all out. Okay, so step one, I'll just multiply this x in here, so I get 10x minus 2x squared. And now I'm gonna have to expand this, so you can use an area model, you can FOIL. And so what we end up here is you get 150x minus 20x, and we get minus, so this would be 20x squared. Then I get minus 30x squared, and then plus 4x cubed. Right, so if I group those, I get 150x minus 20 plus 30x squared plus 4x cubed. And so 150x minus 50x squared plus 4x cubed. Okay, so so far so good, right? We just expanded this thing out, and now what I want to do, if I'm going to find the critical points, as I suggested, is I need to take the derivative of this thing. Okay, so I'm going to go ahead and take my derivative, right? So I'm going to look at v prime of x, and so that's 150 minus 100x plus 12x squared. Okay, and so how would I find the critical values of this function? Any ideas? What would you do to find this? You could factor, yeah, you're certainly going to set it equal to 0, right? So you want to know when it's equal to 0. So Luke says factor, right? So certainly we want to know when this is equal to 0. But if I'm going to factor this thing, so factoring it is reasonable, but on the surface, it doesn't look to me like this is something that factors that easily. So when I look at this, I think to myself, is there a different way? Like, how do you solve quadratic equations? Like, is there some sort of formula that we could use? What do y'all think? Yeah, right. Yeah. So quadratic formula, right, solves quadratic equations. So if we remember, if we recall, right. So let's go to a quick trip down memory lane, right. So negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, right. So we'll have this in our back pocket. This is the solution to ax squared plus bx plus c equals 0, right? So if I want to solve equations that look like this, ax squared plus bx plus c equals 0, I use this formula, right? So what I could do is I would go ahead and we could plug these in, right? So my critical values are x equals negative b, right? So negative 100 is 100. Plus or minus the square root of b squared, right? So negative 100 squared minus 4 times a times c, all are divided by 2 times 12, right? So this number right here, 100 plus or minus the square root of this thing, okay? And so what we can do is at the end of this process, right? So what we're going to do is we're going to look at our endpoints, right? So last time we discussed that we wanted to optimize this on the interval, right? What could x be, right? So we were on the interval 0, right? X could be 0, which means we don't cut into the box at all, and it could go all the way up to 5, right? Which is half, right? So I can take 5 away from both sides, at which point I'd have cut off the entire side of the box here, right? So our endpoints here, our interval is 0, 5, and then we want to check sort of which of our critical points are in this range, right? So as a warm-up, right, we have all the numbers in here, and then what we're going to try to do in the next step is we're going to move and we're going to make a parameter out of this, okay? So let's see how, once we're at this stage, how can we go into Desmos and visualize this, okay? So, right, so we'll go into Desmos, right? So our function v of x is x times 10 minus x times 2x, and 15 minus 2x, and we only want to view it on the interval 0 less than or equal to 5, right? So we have sort of this kind of situation going on, right? And so we wanted to look at certain values, right? So we wanted to look at things that were this: 100 plus the square root of negative 100 squared minus 4 times a times c, right? And then all this divided by 2a, 2 times 12, right? And so we had these two numbers, right? So using these two numbers right here, we see that one of them is 6.37 and the other one is 1.96. And so we can see that, okay, yeah, this is how I would get my optimal value, 1.96. It came out of this quadratic formula. So I want to show you a quick trick here with Desmos. Notice that like this window is pretty bad. So if we type some values into our table like this, there's a zoom fit button, and so we can do a quick trick like this that gives us a nicer window, right? So here's our optimal value, and it came out of the quadratic formula, right? So checking our endpoints 0, 5, and then the only critical number that's in this interval is 1.962. Okay. All right. So we walked through this problem algebraically with how did I get the interval? Okay, so let's jump back over to our Blackboard. All right, so the interval, what happened is it came from looking at the original square, right? So if this distance is 10, right? So if this distance here is 10, and I'm cutting, right? I'm cutting away from both sides. I need this in the middle I need something to be there, right? So I can't actually cut more than halfway down from either side. So like if I cut 6 from either side, then I wouldn't have enough paper there. And so thinking about this problem, right? So this side is longer. So on this side, right, when this is 10, we're cutting away X, and then the most that X could be is I could cut away 5, right? I could cut away half the paper. And so that gives me my upper bound on X, which is 5. And then my lower bound would be, hey, I don't cut anything at all, and that would be X would be 0, just a flat piece of paper. Okay. All right, so the interesting thing about this problem is we don't actually need, right? We don't actually need this to be 15, right? So this number right here, 15, really isn't important for us. Okay, so it could be anything. Like we could have solved this problem if 15 was 1,000 or 22 or 18 or 99, right? So this could be anything. For simplicity, we'll assume that this number is something bigger than 10, right? So our smaller side of our paper is 10. Then we'll have a bigger side, and we just don't know what it is, right? And so we're going to call that thing a parameter, right? So we'll put our parameter here in red, right? So L. Right, so this is my parameter. L is something that's bigger than 10, right? So we'll assume that L is bigger than 10. Okay, so my daughter is doing something out there, but see if you can go through and replace the 15s with L, and I'll come back here in a minute and double check on it, okay? All right. So, all right. So these 15s, as we go through these ones, these should be L's, right? So instead of redoing all of this, what we're going to do is go through and we're going to replace, right, all of these with L's and sort of see how the algebra might work out, right? So this 15 here should be an L, right? So as we're going through, right, we're going to be multiplying these things out, and now at this point, lots of stuff is going to change. Okay, so this and this and this are all gonna change, right? So at this point, what I'm gonna do is, instead of sort of trying to fit these values in, let's go ahead and remultiply this thing out and see if we can make some sense out of this with a parameter. Okay. So so what we're gonna get here is 10 times x times L, right? So this is going to be 10L, that's going to be our number, times x, right? And then we'll get minus 2L x squared, right? And then we'll get minus 20x squared plus 4x cubed. Okay, so as we're thinking through, is this where everybody ended up? Yeah, all right, excellent. So so continuing to go here, right, we'll factor this, right? So we get 10LX, and then we'll get minus here 2L plus 20x squared plus 4x cubed, right? So if we think about this before, what we had a 30 plus 20 in here. If you think about what our work was before, and so this right here, right? This simplified before, right? So this was our 50 that what we had. Right. So this is our 50, and then this was our 150 that's over here, right? Okay. So what we need to do now is we need to go through and we need to take the derivative of this function, right? So our derivative is going to change a little bit. So this is going to change, and then ultimately this is going to change as well. Okay, so our derivative here, when I take the derivative of this thing, right, this is going to be 10L, and then I'm going to get minus 2 times 2L plus 20 times x, and then what we're going to do is, I need some more space here, and then we're going to be adding on a 12x squared. Okay, so this, we just have our parameters in here, right? So we have L's now. And so what I need to do is I need to think about, hey, I'm going to use my quadratic formula again, because this is a quadratic equation, and I have to think about, hey, what my values are here, A, B, and C, right? So our A here is 12. Our B in our quadratic formula is really this thing here, right? Negative 2 times 2L plus 20, and then our C is down here on the end, right? So what I'm going to do is I'm going to go through, I'm going to plug all of these different values into my quadratic formula to get my solution. And notice here what we're doing is we're treating L as just a number, right? So since it is a parameter, it's not a variable in our function, it's just the length, right? So for a particular instance, it's going to be fixed. And we can solve this we're solving this box optimization problem for any box that has width 10 and length greater than 10. Okay, and so that's this L there is acting as our parameter. Okay, so going through here, we have negative b, right? So a negative is going to be a positive. So I get 2 times 2l plus 20 plus or minus the square root of b squared, right? So this is going to be our negative 2 times 2l plus 20 squared. Right, so this is negative b plus or minus square root of b squared minus 4 times a is 12 times c is 10l. And all of this divided by 2 times 12. Okay, so what we're going to see is, again, right, so our interval doesn't change. We could still cut none of the box. We could cut half of our smaller side, which is still 5. And then we have these two critical numbers here that depend on the length, which we're calling L, right? So what we're going to do is we're going to go over and we're going to visualize this in Desmos and see if we can figure out, you know, this problem in its generality, okay? So let's go ahead and share again. All right, so our problem before, right, so we had this one, we had all this set up, but now our equation has changed, right? So this is a slider L, right? And so we said L has to be at least 10, and then it can go to anything, right? So we get a curve that looks like this now, and we're going to try to find this optimal point. Okay. So what I'm going to do is I'm going to put in my formulas here. So just like we had before, but we have a new one, right? So 2 times 2l plus 20 plus the square root of, we have, right, negative b squared, right? So this is b negative 2 times 2l plus 20. So it doesn't want this here, right? B squared minus 4 times A is 12, and then C in our case was 10L. We took this and we divided by 2 times 12. Okay. So this is one of my values. This is the positive side, right? So remember with the plus, we saw that this value was outside of our interval. And then when I take the minus, right, so this value is going to be inside our interval. Right? So as I'm looking at this, I'm going to call this value M, just so it's easier to work with, so I don't have to type all this out. Because this is what I think is going to be the candidate for my max, right? So whatever that point is, right? So this value right here, M, you can see that it depends on the length of my paper. And so if I change my parameter L here, right, so this is the length of the paper, my maximum, it appears to me, is always going to occur at this number right here, right? So what I've done is I've solved this problem without actually knowing what the length of the paper is, right? So if you tell me what the length is, right, so here's our problem, our original problem before, which was this one, right? So we said if our original problem was this 15, right? 10 by 15, so we got this 1.962. But really, you know, I can track where that maximum is going to be regardless of what the length is, right? So we can see that, right, that point doesn't change, right? So I have that one formula there. Okay, so this is this is an illustration of really the power of using calculus. Okay, so some of these problems we can do, right? So if we just set it up, right? So if I knew that L was 15, I was able to pick off that maximum value without really doing any calculus, right? So we didn't have to go through and find critical values or anything like that. But a lot of the time these values are uncertain. And so we have parameters in there. So we're trying to find general solutions that we can manage any situation that would pop up. And so these parameters are a way to do that. And so what we saw is through calculus, using our derivative rules and using our understanding of critical values, that's how we were able to get these values here, right? And so without calculus, we wouldn't have been able to find these values, right? So we actually needed to take derivatives. Okay, so I want to pause here and kick it over to you all, because this is I mean, a lot of what we did here is pretty deep, right? So we've got there's lots of different letters happening, right? So X is our variable, L is a parameter. Lots of stuff going on here. So any questions about this, where these came from, sort of, so what we're doing? Good, bad? We're good? Okay. So, so let's go back and then check out what we're doing in our book, right? So, so this was a problem from 3.3 down toward the bottom, right? So we're optimizing this cardboard. And then, so what I did is I kind of turned this problem on its head, and we looked at it with a parameter, right? So to me, that's the real value here of calculus, is being able to do these things with parameters. Okay, so what I want to do now is continue with the optimization problems, right? So we're going to jump into section 3.4, and this sort of discussion, this note 3.4.2 is going to be really helpful for students, and it's sort of the process that we've walked through over our last few examples, sort of what you're doing when you are solving these optimization problems, right? So step one, draw a picture, introduce variables, right? We're trying to understand the situation, what's going on, right? Identify any equations. We were writing those down, so that's kind of like what we did with our volume. So we're going to see here, right? So sometimes we're going to have multiple variables that are in there, and so we want to use some constraints to reduce that to a single variable. We consider domains, and then we found our max and mins. Right? So this process right here, if you're thinking, right, when you're doing these optimization problems, this is a helpful guide to what we're going to do here. Right? So I want to jump into this next activity where we're going to introduce a cost. Okay, so a lot of students, particularly in calculus, are interested in sort of the business side of things or the economic side. Especially at Westfield, we've got lots of math, econ majors and actuarial science majors. And so what we're going to just think about this activity where we introduce a cost, and we're going to try to minimize the cost of a soup can. Okay, so you can envision here that you are, you could be in manufacturing, and you have some kind of soup company, and what you want to do is you have the ability to change the shape of your can. Okay, so it's a can is this cylinder, and so we're going to say that your soup, right? You're selling some soup, and you have to have a fixed volume for your soup can, right? So they're giving us in this activity, you want to sell volume that is 16 cubic inches. Okay, so this 16 cubic inches here, that's going to be fixed, and so you just have to make sure that your can holds the right amount of soup, but you can change the dimension, right? So it could be fatter, it could be like a really wide can and short, or it could be like a really skinny can and it could be tall. You just want to make sure that it holds the right volume. And so the other parameters that we're given here is the sides of the can have one cost, and then the top and the bottom, the lids, have another cost, right? So So presumably here the lids cost more because they're sturdier, right? So the top and the bottom of the can, we're going to build those out of a sturdier material. That costs a little bit more, and the sides is a little bit less important, so it'll cost a little bit less for that material for the sides. Okay? And so what we would like to do is figure out the optimal situation, right? So what are the dimensions of the can that minimize cost, right? So if you're making this thing, you want to have the absolute minimum cost of the can under the constraint that it holds the right amount of volume. Okay, so there's two kind of things that we're considering here. We have a quantity that's going to be optimized, which is cost. We have a constraint function, which is what we have to work under. Okay, so all of these problems are going to have some sort of constraint, because if there's no constraint, then there's no sense of optimizing, right? If you have unlimited resources, then you can do whatever you want, right? If there's no constraints, then there's no need to optimize. Yeah. So let's record some of this information, right? So we need 16 cubic inches, right? That's our volume that we need. And then the top of the can, and then the sides of the can, right? So we'll record this over to our Blackboard, right? So the side of the can costs $0.015 per square inch, and then the lids cost $0.027 per square inch, right? So we want to minimize cost. So let's jump back over here, Blackboard. So here's some notes for us to think about. All right, so a can, right? So a can, something like this, right? So it's a right circular cylinder, right? So we have a can that looks something like this, and we want to figure out, what are the dimensions of this can. Okay. So let me kick it over to you. What are we thinking about here? So what are some of the things that we need if we're going to study this can? Like what measurements should we make? And what equations do we want? What information do we want to know about this can? Yeah, the height, right? So the height is going to be one of them, right? So certainly how tall the can is going to be important. And then what else? So height is crucial, right? How tall it's going to be. And then also so for everybody watching on YouTube, just so you know, I don't know that you can see the chat, but the students are also in the chat here. We're giving me feedback. So if you see me sort of answering questions that you don't hear, they're typed in as text. So the height here, right? So you have the height of the can, and then the length of the base, right? So you could think about that, right? So you could think about it as the length of the base, or how wide it is. So since this is a circle, right? We have a circular base. We're actually gonna consider the radius, right? So if I know the radius of that circle, then double that would be the length. Okay, so you could use the diameter of the can, but a lot of our common formulas for circles and things like this, they use radius. So I'm gonna go ahead and use radius. Okay. So some other things to consider over here, right? So the units on these things, inches squared. So volume is cubic inches, right? So that's going to be our volume. But when you think about the sides, the top and the sides, the cost of these things, they come in square inches. So when I think about inches squared, I'm thinking area, right? So So area is going to be, right, is going to be in here somewhere. So for the top, if I'm going to think about cost in terms of inches squared, I'm going to need to know the area of the top here, and I'm going to need to know the area of the bottom. And what I'm going to need is I'm going to need to know like the area all the way around of this can, right? So we think about a circular cylinder, right? So if I think about a piece of paper here, right, just to make it into a cylinder, right, I'm going to need to know the top area, the bottom area, and the area for the sides. Okay, so one helpful thing when thinking about a cylinder is like what would happen if you unfolded it, right? So if I deconstructed this can, what would happen is, right, I could pull the top off, that would be a circle. I could pull the bottom off, that would be another circle. And then if I sort of made a cut down the side of the can and unfolded it, I would get a rectangle, right? So sometimes when you think about problems like this, you would try to think about a net of your 3D object. And so that might look something like this, right? So if I were to unfold my can and lay it flat, it might look something like this, right? So you can imagine sort of rolling up that rectangle and then putting the lids on the top and the bottom to get your can. Okay, so in the context of this problem, just trying to make sense of it right now, right? We have this thing. This is R, right? So that's our R. That's the radius of our can, and this is R down here. And then our height, right? So our height would be over here. Okay. All right. So we haven't done any calculus, so we're just sort of talking about this problem, trying to make sense of it. So what else do we need? We would need. I would need, I think, coming over here for volume, 16 cubic inches. Maybe I want to know what's the volume of this can. So volume, if we remember, so a good thing to think about is when you're finding the volume of a, so generally a prism here, but so you have a shape where you have a fixed base and the sides go straight up. Anything that looks like that, what you can do is you can find the area of the base and then multiply by the height. And so the volume is going to be the area of my base, so the area of that circle, which is pi r squared. And then I'm going to multiply that by my height. Right, so this is pi r squared times h. Right, so that'll be the volume of my cylinder. And now if I'm thinking about area, I'm going to need to know what the area of my sides are and the area of the top and the bottom. Okay? So if I think about the surface area of this can, the top, right? So this gives me a pi r squared here. Down here, I get another pi r squared. That's my area. And then I guess the question is, what's the area here? So it's going to be length times width. And so there's going to be an h in there, but any ideas on how I might find this distance right here? Yeah, right. Circumference. Exactly. That's exactly right. So this red right here, right? So this red distance is going to be the same as all the way around, right? So going all the way around the circle. But so you can imagine, like, as that side wraps around, it's going to take the whole circle, right? So this is the circumference of a circle is 2 pi r, right? And so my surface area, which I'll call SA, is going to be right the top, pi r squared and then I'm going to plus another pi r squared, so I get 2 of those. And then I'm going to get the length times width here, which is 2 pi r times h. Okay, so my surface area, so we've got the volume up here, and I've got my surface area. And okay, so what else do we need for this problem? What were we trying to minimize? Let's jump back really quick and then look at our problem, right? So we did a bunch of sort of planning. We did this, right? We drew a picture, we labeled dimensions and variables. So then we want to use our variables to determine volume, we did that, surface area, and and cost, right? So this is what we want to minimize. What dimensions minimize the cost of the can, okay? Okay, so once we do that, we're going to set it up and it says, hey, we're going to have to put this into a single variable. So let's go back. Right, so we need to figure out our cost. Right, so here's a bunch of information for us that we figured out. But what's the cost? Okay, so cost, that's a new thing that we want to think about. Well, it's going to be, let's see, it's going to be how much stuff we have up top here, right, and down here, down at the bottom, right? So how much stuff we have in the circle times the cost of that. Did I flip these? Didn't we say that the top and the bottom cost more? I think we flipped this, right? So I believe we said that the top should cost more, right? So this is the sides and this is the top lids. Okay, so as we're going through, right? So this is going to be the area here times the cost of the lid plus the area here times the cost of the sides, right? So what we should get is right. So this is for the top 0.027 times 2 pi r squared plus 0.015, that's the cost of the sides, times how much stuff is on the sides, right? All right, so this is our cost function, and it looks like our cost function depends on certain things, right? So the cost depends on, it depends on the radius and the height, right? So if you were to give me the radius and the height of our can, then we could figure out the cost here. But this is Calc 1, so we aren't doing multivariable calculus yet. So we will see multivariable calculus when you get to Calc 3. But fortunately for us, what we have is we have a constraint, right? So we are working under a constraint here. And so what we'll find is we can actually use this volume formula to eliminate one of these variables, right? So this radius here, this is an R, this is an R, and we have an H. So I could choose one of these to get rid of. We'll see how to do that in a moment, but since there's only one H, I'm gonna choose to get rid of my H over here, okay? So using our constraint, we know that the volume, right, so pi r squared H, this is our volume, has to be equal to 16. Right, so pi r squared H has to be 16. And so what I can do is I can set this up, right? So I can set my whole equation up and I can solve this for H, right? So H has to be equal to 16 divided by pi r squared. Right? And so what we're gonna do is we're gonna take this H right here and we're gonna substitute it in for this H up here in the top right. So what this will do is when I make that substitution, I'm not going to have any variables except for the radius. my can, right? So my cost function based on the radius is going to be 0.027 times 2 pi r squared plus 0.015 times 2 pi r times 16 over pi r squared. Okay. And so just doing some simplifications here, right? So these pi's I think will cancel. One of these r's will cancel. And so to make our lives a little bit easier, our cost function based on the radius is this 0.027 times 2 pi r squared plus 0.015 and then times this 32 over r. Okay. All right, so we have our cost function. So this is sort of our information so far. We have our cost function, and we want to think about, hey, what kind of interval do we want to optimize over? Right, so we think about our radius here. Right, so our variable is r. So what could r be, right? So it's certainly, we're not going to have a negative radius. But if we think about, is there any sort of minimal value? But I could make my cylinder really, really, really narrow, and then it would just continually be taller. Or I could make it really, 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 really wide, and it would just be really short. Okay, so the interval that we're gonna optimize over is just this, right? So r could be anything positive, and it could be as big as we want. Right, so we're going to just consider positive values. So we're basically out of time here. So instead of doing this out algebraically, let's go ahead and put it into Desmos. Okay, so we'll get a new graph here. And just so we have some closure on this, let's go ahead and optimize it, right? So we're going to call this C of r, and then we'll get 0.027 times 2 pi r squared, right? So we had it looking like this, plus 0.015 times 32, and then over r. And we said we only want to consider this when our r value is positive, right? And so it looks like what we have here is, right, so we graph this, we set it up, and then if we look, it seems like we should see that we have one critical value, and we should have this down here, right? So interpreting this, right, so it would cost us, about $0.641 per can, and then the radius we should have is about 1.123 inches, right? So when we look at this, remember we're only able to do this in Desmos because we have these costs, right? So you might want to set up different situations where these are parameters. So if I wasn't sure how much the lid was going to be, right? So this could be a parameter, right? That could be a C, right? So the cost of the lid, or this could also be a parameter. They could both be parameters. We could still do this problem in generality and set this up, right? But for us here, minimizing the cost is going to come when we have a radius of 1.123 inches and a height of right, so we could plug our radius back into our formula for height, and then our height would be about a little over 4 inches here, right? So you'd have a 1.1 and an eighth maybe by 4 inch can, and that would give you your optimal dimensions to minimize costs. Okay, so keep in mind, right, sort of the structure that we did here when you're working through the different problems, right? So what we did was we drew a picture, right? We set up our problem, and we thought about all the different dimensions that we needed, and we came up with some formulas, right? So for volume, for surface area, and for cost. And then the next step was, hey, our cost function has multiple variables. It has R's and H's in it. And so what we did is we used our constraint, right? Our constraint was a fixed volume to eliminate one of those variables. And then we were able to optimize our new cost function. Okay, so this general procedure is one that will work for your optimization problems, and it's outlined here in this note. So this might be something that you want to go back to and think about as you're doing the homework problems. Okay, so on Friday we'll continue, right? We'll do some more optimization problems. We'll think about some stuff that has some geometry in it. We'll do a 2-parameter optimization problem, and we'll do some stuff with trigonometry in it as well. Okay, so this is our plan for Friday. Work through 3 more optimization problems, and so I'll kick it over to you all. If there's any questions, I can field them here, and if not, we can call it for this day. So I think any questions here about this stuff? All right, so I'm gonna call it here, but we'll pick this up, right? So we'll do some more optimization problems on Friday. So hope you're all staying safe, and I'll see you. Thanks again. Have a great day too.